Leave an apple on the counter, and it eventually rots. Pour a glass of milk, and within a few days, it ferments and sours. It is a strict biological rule that any organic matter, left exposed to the elements, will break down and spoil. Yet when archaeologists unsealed tombs in ancient Egypt, they found simple, unassuming clay jars, sitting perfectly intact for over 3,000 years. Inside those jars was a thick, golden liquid that was completely, perfectly edible. This creates a strange paradox. That immortal substance comes entirely from plant nectar, a sweet, highly watery liquid that is incredibly fragile. If bees simply gathered that raw nectar and poured it into their hives, its high moisture content would immediately invite yeast and bacteria. It would ferment and turn sour. To survive the freezing winter without their food supplies rotting away, the honeybee colony has to act quickly. They must execute an intense, multi-step process of chemical and physical engineering to turn that watery nectar into something that essentially lives forever. The process starts outside in the fields. A female worker bee, acting as a forager, lands on a bloom to search for that watery plant nectar hidden deep inside the flower. To reach it, she relies on her specialized anatomy. She extends her proboscis, a long, flexible, straw-like tongue perfectly designed to suck up the sweet liquid. This diagram illustrates exactly where that nectar goes. Notice that the bee doesn't digest this liquid for her own energy. Instead, she routes it into a specialized internal pouch called the honey stomach, completely separate from her normal digestive tract. Once inside that pouch, the first biological defense against spoilage activates. The stomach releases an enzyme called invertase. This enzyme attacks the complex sugars of the plant nectar and splits them into simpler, more stable components like glucose and fructose. As she turns back toward the hive, her honey stomach operates as a mobile chemical refinery, actively altering the nectar's composition while still in flight. When her honey stomach is finally full, the forager leaves the sunlight and returns to the dense, packed hive. She delivers the nectar directly into the mouth of a younger processor bee, a social transfer that keeps the liquid isolated from the outside air. This processor bee takes over the refinement. For roughly half an hour, she continuously passes the nectar back and forth in her mouth, deliberately infusing it with even more enzymes produced by her own head glands. This animated scale shows the chemical shift occurring during that half hour. As the bee processes the liquid, those added enzymes create trace amounts of gluconic acid and hydrogen peroxide, taking the nectar from a neutral state into a highly acidic one. This deliberate acidification creates a harsh environment that bacteria simply cannot survive in. The raw nectar is now actively hostile to the very microbes that would cause it to rot. Even with these intense chemical defenses in place, the colony still faces a massive physical problem. The liquid is roughly 80% water, meaning it's still far too moist to be stored long-term. To solve this, the processor bees regurgitate and carefully spread the watery, acidic syrup across the broad surfaces of the empty hexagonal wax cells. Then, thousands of bees act as a living, breathing ventilation system. They stand directly over the open chambers and rapidly beat their wings to generate a massive, continuous draft of warm air throughout the entire structure. This chart tracks the mechanical effect of that massive draft. The constant airflow physically evaporates the excess water right out of the nectar, driving the moisture level rapidly down below 18%. Once the liquid has thickened into that dense, sticky syrup, the workers cap the cells with an airtight seal of fresh beeswax. Combining acidic chemistry with extreme dehydration, they have secured a food supply that can outlast the harshest winter. When you step back from the microscopic chemistry, the mathematics required to keep an entire colony alive this way are staggering. This diagram highlights the lifetime output of an individual worker bee. Flying back and forth day after day, her entire life's work will produce just 1/12 of a single teaspoon of honey. To produce just 1 pound of honey, a colony has to collectively visit roughly 2 million individual flowers. The combined flight distance required to gather that much nectar is the equivalent of orbiting the Earth 3 entire times. This relentless, high-volume pursuit of nectar forces honeybees to constantly brush against pollen. As they move from bloom to bloom, they act as a massive engine for pollination, unknowingly sustaining the crops and plants that feed the world. But this delicate, ancient system is currently under severe stress. Habitat loss continues to shrink their foraging grounds, while the widespread use of agricultural chemicals poisons the insects mid-flight and disrupts entire colonies. A simple jar of honey sitting in your pantry represents millions of miles flown, thousands of hours of chewing, and a perfect sequence of biological reactions. It is a masterpiece of evolutionary chemistry and collective labor, an immortal resource that we have an ecological duty